You laser scan the part. Polyworks analyzes the quality of your scanning session, and guided by the analysis results, you go back to the part and you enhance the measurement. When you go out, when you shut down your scanner and you finish measuring the part, the job is completed. So we will go one step down below and look at some of the aspects of the scanning, the analysis, and the enhancements. So, and let's first start with the real-time meshing process. We believe that real-time meshing is a fundamental aspect of our new technology, of our new platform. The reason why we believe that, there are three important reasons. So let me show each of these reasons. First of all, it's related to getting the optimal data quality for a given scan data files. But before talking about this picture, I'd like to talk to you about how laser scanners works. In a laser scanning system, you have two components. You have the laser scanner itself that measures a line of points, and then you have a localizer, a system that is used to localize the scanner everywhere in 3D space so you can make scans of surfaces. For example, the localizer could be an arm or could be an optical tracking system. So this means there are two sources of uncertainties in a laser scan system. There is a noise caused by laser scanning data itself, the laser scanning sensor, and there is the uncertainties related to the use of the localizer technology. And this produces the following effects. When you do multiple laser scans of a part, there are gaps between scans. So, and these gaps are normal. That's perfectly acceptable, but the gaps could be in the order of 25 micron, 50 micron, even 75 microns. That's something normal. So what's the effect of a gap? Let's look at this picture. We have two scans here. One scan is like that, and then you have another scan like that, and there's a gap between those scans. If you look at the areas where there is no overlap, the scans look pretty nice and smooth. But when you have an area of overlap, it looks like two layers of points. So if you're working with the scan data as a point cloud data set, what happens? You see multiple layers of data points. And there are some metrological processes that don't like this kind of data sets. For example, GD&T. GD&T is very sensitive to outliers. So it's not the ideal representation for GD&T. What's the advantage of having a meshing strategy like the Polyworks meshing? We can create a surface like the blue surface. Look at the blue surface, how it makes a smooth transition between the left and right scans by intelligently averaging and blending the scans together. Instead of having two layers of points in the overlapping area, we have a transition surface that makes a smooth transition. So we argue that this is a best fit compromise. It's a mesh that is a better compromise than using the raw data set. And for several metrological processes, such as GD&T, but also any type of gauging, such as airfoil gauging or profile gauging, flush and gap, we think that this is a better way to describe the real data. Of course, a very obvious advantage of using a mesh is it makes missing areas where data are missing very obvious. So you can see holes in the data sets and go back with a scanner and fill those areas. Finally, as we mentioned before, our platform is based on quality metrics, and we need to indicate to users areas where quality is lower. So we think that it's easier to display those areas on polygons because polygons fill the screen. If we would have point clouds, we would see some dots or some small squares on the screen. It would be more difficult to perceive the colors. So we've reviewed a little bit about the meshing process. Now let's talk about quality metrics and how we can use them to highlight areas of lower quality. The first quality metric that we've mentioned already is the scanner to surface angle. It corresponds to the blue color in the demonstration that I've just made. It's important to control the angle between the incoming laser light and the surface normal because it has two impacts on the scan data. First impact has to do with the resolution or the point-to-point distances you get on the part. The smallest point-to-point distance will always be achieved by scanning at a 0-degree angle. As your angle increases and increases, you're going to follow a rule of the inverse of the cosine of the angle, which means that at 60 degrees, for example, your point-to-point distance will be twice as large compared to 0 degrees. If you are at 75 degrees, it's going to be 4 times larger. You thought you were scanning at 0.1, but in fact you are scanning at 0.4. So that's a major difference and could be problematic under some circumstances.